Okay, 6.13, improper integrals. Improper integrals are integrals with finite limits of integration. For example, if we have the integral from 1 to infinity of 1 over x dx, or have a infinite discontinuity on the interval. So for example, the integral of -1 to 1 of 1 over x dx, because within that interval, -1 to 1, we have 0. And if we plug in 0 for x, we have 1 over 0, which is undefined. So two examples of improper integrals. If f of x is continuous on closed interval a to infinity, then the integral of a to infinity f of x dx is equal to the limit as t approaches infinity of the integral a to t f of x dx. And if f of x is continuous on negative infinity to closed b, then the integral of negative infinity to b of f of x dx is equal to the limit as t approaches negative infinity of the integral t to b f of x dx. Of course, provided that the limits exist. So looking at number one says the integral of 1 to infinity of 1 over x to the 4th dx. Well, I can first rewrite this as the integral of 1 to infinity x to the -4 dx. Okay, and then since I have an infinity in my integration, I'm going to use that limit as t approaches infinity. So the limit as t approaches infinity of the integral from 1 to t x to the -4 dx is equal to the limit as t approaches infinity of x to the -3 over -3 solved at 1 and t. Well, this is equal to the limit as t approaches infinity of, let's see, we have -1/3 times 1 over t cubed minus, and then another -1/3 times 1 over 1. So if we look at t, since t is on the denominator, because I moved it there because we had a -3 as the exponent, if we approach infinity for t, that means that denominator is going to get very large, which means this section here is going to approach 0. So I have that this is 0 plus 1/3, which is equal to 1/3, and that is the answer. Okay, this next part says, if the limit exists, the improper integral is said to converge. And if the limit does not exist, the integral is said to diverge. So if we look back at number 1, notice that our limit did exist because we ended up with a number. So that means that this integral is going to converge. Okay, now let's answer number 2. Number 2, we have the integral of 1 to infinity of 1 over x dx. Well, this is the same as saying the limit as t approaches infinity of the integral of 1 to t of 1 over x dx, which is equal to the limit as t approaches infinity of the natural log of the absolute value of x solved at 1 and t. Okay, this is equal to the limit as t approaches infinity of the natural log of absolute value of t minus the natural log of absolute value of 1. And if we plug in infinity for t, the natural log of infinity is going to just continue to increase rapidly, so it's going to approach infinity. And the natural log of 1 is 0, so infinity minus 0 is equal to infinity, which means that this limit doesn't exist, so we say that the integral diverges. Okay. Okay, if we're dealing with an improper p integral, so for example, the integral of 1 to infinity of 1 over x to the p, so p as an exponent, dx, converges if p is greater than 1 and diverges if p is less than or equal to 1. And if we look at the examples above, in the very first example, we had 1 over x to the fourth. Well, the p-value of 4 is greater than 1, so it converges. And then on number 2, we had 1 over x where the p-value was 1, and since 1 is less than or equal to 1, it diverged. So it kind of just proves what we just did on number 1 and number 2. Okay, it says, remember the definite integral a to b f of x dx requires the interval to be finite, and the fundamental theorem of calculus requires that f of x to be continuous on that closed interval a, b. If the integral does not meet these requirements, we may have to manipulate the problem. So another form of an improper integral is if we have the integral of negative infinity to infinity f of x, and f of x is continuous on negative infinity to infinity, then we could rewrite this and separate it into two integrals using some value c. Typically, c is going to be 0, because 0 is in between negative infinity and infinity. So looking at number 3, we could write this as the integral from negative infinity to 0, e to the x dx, okay, plus the integral of 0 to infinity, e to the x dx. Then we could take the limit as t approaches negative infinity of t to 0, e to the x dx, plus the limit as t approaches positive infinity of the integral of 0 to t, e to the x dx. Integrating this, we get the limit as t approaches negative infinity of e to the x solved at t and 0, plus the limit as t approaches infinity of e to the x solved at 0 and t. So we get the limit as t approaches negative infinity of e to the 0 minus e to the t, plus the limit as t approaches infinity of e to the t minus e to the 0. Remember, e to the 0 is just 1, okay? And then for each of these e to the t values, let's say we substitute infinity or negative infinity in. If we have e to the t, and this is e to the negative infinity, this is technically 1 over e to the infinity, which is going to approach 0. Okay, and then over here, this is e to the infinity, which we know is going to approach infinity. So really, we have 0 plus infinity, which is infinity, so the limit doesn't exist, and this is going to diverge. Okay. Now it says if f of x is continuous on closed A and open B and has an infinite discontinuity at B, then we say that the integral from a to b f of x dx is equal to the limit as t approaches b from the left of the integral a to t f of x dx. And if the opposite is true, so if f of x is continuous on the open interval a, closed interval b, and has an infinite discontinuity at a, then we say that the integral from a to b f of x dx is equal to the limit as t approaches a from the right side, integral of t to b f of x dx. So using that information, we're going to solve number 4. And number 4, notice that we go from 0 to 2. Well, if we were to plug in 0 into this equation, notice that all of this would go to 0, and then we would end up having 2 divided by 0, which is undefined. Okay, which means we have an infinite discontinuity at 0. So I would rewrite this as the limit as t approaches 0 from the right, integral t to 2, x plus 2 over the square root of x squared plus 4x dx. Okay, now that I have it in terms of the limit, I'm then going to use substitution. So let u equal x squared plus 4x, everything under that radical. So du dx is equal to 2x plus 4. So dx is equal to du over 2x plus 4. Or we can say that this is du over 2 times x plus 2. So I have the limit as t approaches 0 from the right of the integral from, and now I have to plug in these values into u to get my new integrals, my new bounds. So 2 for x, I have 2 squared, which is 4. 4 plus 4 times 2, which is 8, so I have 12. And then here I have t squared plus 4t of x plus 2 over the square root of u du over 2x plus 2. So x plus 2 cancels out, and I can take out that divide by 2 and make it a 1/2 in the front. So this is equal to the limit as t approaches 0 from the right of 1/2 integral of 12 t squared plus 4t, okay, of 1 over the square root of u, well, that's u to the negative 1/2 du. Okay, then I can integrate this. And so I have the limit as t approaches 0 from the right of 1/2 u to the 1/2 divided by 1/2, solved at 12 and t squared plus 4. The 1/2s cancel, and so I end up getting the limit as t approaches 0 from the right of the square root of 12 minus the square root of t squared plus 4t. Okay. Well, if I take the limit as t approaches 0 from the right, this whole thing is going to go to 0, which means I have my answer as the square root of 12 minus 0, which is the square root of 12. So that means my limit exists, and this integral is going to converge. Okay. Lastly, number 5 says if f of x is continuous on the closed interval a, b, except for some c in the open interval a, b, at which f has an indefinite discontinuity, then we could rewrite it as such. So almost exactly how we did number 4, where we separated it into, was it number 4? No, sorry, number 3, where we separated it into 2 integrals because we had negative to positive infinity. We're going to do the same thing here because we want to get rid of that infinite discontinuity at 0. So I can rewrite this as the integral of negative 1 to 0, 1 over x dx, plus the integral of 0 to 1, 1 over x dx. So I can write this as the limit as t approaches 0 from the left, integral negative 1 to t, 1 over x dx, plus the limit as t approaches 0 from the right, integral of t to 1, 1 over x dx. So then I get that the limit as t approaches 0 from the left is going to equal the natural log of the absolute value of x solved at negative 1 and t, plus the limit as t approaches 0 from the right of the natural log of the absolute value of x solved at t and 1. So I have the limit as t approaches 0 from the left of natural log absolute value of t minus natural log absolute value of negative 1 plus the limit as t approaches 0 from the right of natural log absolute value of 1 minus natural log absolute value of t. Okay. We know that this is going to end up not existing because if we were just to look at the natural log, let's say the limit as t approaches 0 in general of the natural log of absolute value of t, well, there is no value where t is going to approach 0 because the natural log of 0 is undefined. So we would say that this does not exist since the natural log of 0 is undefined. Okay, and if this limit doesn't exist, then we can say that this integral is going to diverge.